All right, welcome back. Here we are again looking at this maximization problem from last time. I started right off by writing it in this recursive form where v is defined in terms of itself. And this v is what we're going to be referring to throughout this course as the value function. So it's a function that tells you what is the value of the maximization problem. Once we've solved out what is the optimal rule for the agent to follow, we're going to refer to that as the policy function. All right. You may also recall from last time that I said that one way that we're going to be able to think about this value function is as the limit of the following sequence. Give me some kind of v, any function from an appropriate space. We'll discuss that now. And define b of v as what happens if this agent thinks that the future is defined by this small v. Now, one way to get more specific about this is to say, let's assume that you're forcing the agent to follow some particular policy function from next period on. Of course, you know for sure that that v can't exceed the maximum achievable with the value function. And then b of v is the optimal behavior, assuming that in the future you're going to follow some fixed rule that may or may not be optimal. We can apply this operator big B repeatedly. If we start with v0, we apply it once, we get v1. We start with v1, we can apply it again, we'll get v2, and so on. And I claimed last time that, well, we would like it would certainly be convenient if repeating the Bellman operator, the application of the Bellman operator over and over and over led to a sequence of functions that converge to what we actually want. Now the question is, how do we define distance, or convergence rather, between functions? In order to have a notion of convergence of functions, we have to have a notion of them getting closer and closer together. We also need to have a sense of the space in which those functions live, the set where they come from. So now we'll be a little more careful about that.